What's up, guys? It's June 24th, 11:30 a.m. Um, yeah, let's get into it. Um, I kind of want to get into the trees because that's what I'm the worst at. I guess we can do task scheduler and let's get into the trees because the trees is like guaranteed they're gonna ask this, right? Invert binary tree. Wait, let's do the task scheduler first. Yeah, so today is just a grinding day. I really want to finish lecture 5A and get to programming my FPGA because I think that's going to be very fun. So let's do it. You are given an array of CPU tasks, each labeled with a letter from A to Z. Oh, also a little bit of update. Yesterday's interview went great. Brian, my guy, said he's going to put me through the next round and also told me to study up on A/B testing. Um, some metrics of trading products such as trading volume, such as MAU, such as trading frequency, et cetera, et cetera. Retention rate, things like that. So pretty product management things. So once I get the interview, I'm going to start prepping for that. Other than that, another friend of mine, old colleague of mine, asked me if I want to work with him on project. That's pretty cool. So yeah, I mean, you know, Cheval, very smart guy, very smart guy. Uh, so yeah. Anyways, let's get into it. At a number N. Okay. How does a heap come into this? How does a heap come into this? Hmm. Yep, that's what I'm thinking as well, using some sort of frequency. Right. So I track down the frequency of the most frequent element. So for example, A, then then it has to be N N, A N N. So however many frequency the most frequent element is, right? So I could be B X B, something like that. use priority queue. If I have a priority queue of Okay, so I'm thinking there has to be at least the max frequency times n, right? At least. So this will be at least 3 times 3 because it has to be at least A and then XXX, A, XXX, A, and then whatever, right? So it has to be at least this, which is 9. So this is the floor, right? Find the most frequent element that can be placed within this cycle. Ah, okay. I think I kind of have an idea. So I have vector int, right? I have a vector of ints of letters, and then they will be of size 26, and they will all be 0, right? And then this would be my list of available characters, right? And then I will have a priority queue of ints of a pair of character and int. I'll call this max heap, right? Char. Character minus A is not equals to 1. If it is equals to 0, then I'll set it to 1. Right. So now I'll have all the letters that are available. Why would I want to use a priority queue exactly? Hmm. Do I even need the letters? It doesn't seem like I need the letters. Okay. So while max seat is not empty, wait, so the floor would be, right? That's the floor. While it's not empty, um, right, it would be something like this. Right, it would be something like this. It would be the minimum would be 2. No, the minimum would be 3, right? AXA 2 plus. No, but then the floor will be wrong. What's wrong here? Three plus 2 times n. 3 plus 6 equals to 9. 2 plus 1 times 1, so it's 3. Okay, yeah, that floor is correct now. So I have the floor, which is the minimum amount, right? And then I would pop the first element. So that's out of the equation now. What if there's only 2 B's? Yeah, I don't need letters. I don't. If I use a heap, then I don't really need letters. Um, what is the cheese here? What is the cheese here? What is the trick? What if it's A, A, B, 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 C, C, D, 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 right? Then what happens? I'm not sure, fam. That's pretty genius, actually. Okay, don't want to do this. Don't do this tomorrow. Um, no, invert binary true. Like this is what I really need to work on because I'm very bad at this. How the fuck do I do this? I completely forgot. What's this? If the root is null, then I return yes. And then I will create a temporary root, which is the left root, which is the left node. The left node will be equals to the right node. The right node will be equals to the left node. And that changes it. The right node will be equals to, oh, wow. Okay. That makes a lot of sense, actually. See, seems to be such an easy thing to do. Okay, so if else, what would happen if I went this first? Does it matter? I don't really think it matters, right? Yeah. Okay, cool. Cool, cool, cool. What about this? The length of the diameter. 4213. Okay, so it's kind of the depth, right? And then, fuck, how do I find the depth? I'll just make it traverse the left, traverse the right. What if I just go? Is that correct? Why is this right? I don't even wait, what? It shouldn't be right. I don't know, bro. I'm so bad at this. Wrote this half asleep. Tainubila. What the fuck? I follow, but I don't really know how he came up with that, bro. Like that's the part where I don't get the most.
Hey everyone, welcome back. And let's write some more neat power of length through the root would be 2 plus 1, which is 3. But keep in mind that the longest path might not necessarily run through the root. So let's look at a counterexample. With this tree, if we try to calculate the diameter through the root, on the left side we have nothing, so that's a 0. On the right side we have 3. That's the longest path. You could take multiple different paths, but all of them are going to be of length 3, so the diameter from here is 3. But consider the node over here. Length on the left side is 2, and length on the right side is 2. So total is 4. That's the diameter of this tree. Now, I want to mention to you that this problem is actually closer to a medium problem than an easy problem. Why exactly is that? Because the solution initially seems pretty obvious, right? To get the result, we can just try to calculate the diameter through every single node in the tree. How do you do that? Well, just like I did, get the longest path on the left and the longest path on the right and add them together, aka sort of like the height on the left side and the height on the right side.
Yeah.
Generally, we do this recursively with some kind of DFS algorithm. But the tricky part about this problem is that the return value, obviously, of this DFS is going to be the height. So what we want to return from this right subtree up to this node is, of course, the height. But that's not the result that we're ultimately trying to compute. What we're actually trying to compute is the diameter. Now, in terms of the code, there are multiple ways of handling that. The way I'll show you is sort of by using a member variable, or you can even think of it as sort of a global variable with respect to the recursive function. But the algorithm will be exactly like this. Recursively run DFS. From the left subtree, we reach null. So the height of that, of course, is going to be 0. That's what we return up here. Then do the same on the right side. And then we continuously go down. And so here we reach the case with just a node. The height of that we will say is going to be 1. That's going to be returned up to the parent. And that's basically saying that the length of this is 1. Same thing for this side, but the length is 1. So now when we want to compute the diameter from here, we're going to maintain a global variable, which I'll call it the result, or this for short. And initially we'll set it to 0. This is what we're trying to maximize, of course. And from this node, we calculate a diameter of 1 plus 1, which of course is going to be 2 now. That's the biggest result that we have. Now, from this node, I want to return up to my parent the height of this tree. So what do I do? Well, the height is different than the diameter, so we actually will take the max of the left subtree, the max of the right subtree, and add 1 to it. Well, in this case, they're the same, so we just get 1 and then add 1 to it, which is this edge. So we'll say that the height.
Oh.
Obviously, it didn't have to be like that. Suppose there was a node over here, and then maybe the height of this right tree would have been 2 plus 1, which would have been 3. So that's generally the core idea. We would do the same thing from here because it's kind of symmetrical to this side. So this would be 1 and 1. And then the height of this is 2. Height of this is 2. Those are going to be returned up to 3. Add them together. The diameter now is going to be 4. It's going to be increased all the way up to 4. From here, we want to take the max of left, max of right, it's 2, and we want to add 1 to it because of this edge here. So then we say the height of this part is 3. We return that up to the root. I'll make it another color, 3. Root is going to do the same thing, take left plus right, add them together, we get 3. This time it's not greater than the result. So our result will stay unchanged and it will be 4. 4 is ultimately what we would return, but it's not going to be returned from the recursive function. Keep that in mind. We're going to have a separate variable that's sort of going to be global, which does that. And since we were able to accomplish this by just visiting each node once, we will say that the time complexity is linear. Base complexity is going to be proportional to the height of the tree, which could be log n for a balanced tree. or n for a non-balanced tree. So we're going to solve the balanced tree or n for a non-balanced tree. So we're going to solve this recursively, and I like to do it with nested functions. So I'm going to have
Okay, well, I understand because you're keeping track of two different variables, right? Um, because you're keeping track of two different variables. So it's kind of you will return the height. That's right. Something like that. Yeah, these two are the cheese. Or the cheese. Like that's the technique there. There's these two lines. This is pretty standard. Like, yeah. Okay, whatever. Okay, whatever. Yep, call it a day here. Gotta watch lectures and do my PJ stuff.
刚是公告冰玩的，
邊個？
你今日公告㗎，
我 interview
琴日嗰個。
啊
No anxiety, leaving next round.
啊
That's right. Good job. Good job. Happy for you, man.
我都是那個
Yeah.
I'll get it.
Wow. Not wacky, but so slappy. Just-
係咯，
哇！我今日痛到爆個心，我完全唔知點解。
你啱啊。
唔係啊，本身以為係 free drive 㗎，guess what？